Matrix A is equal to alpha of ij, and we give the dimensions outside, and we can have a rule defining it, which is why this notation is useful. So for example, we can say that the matrix A is defined by the rule that alpha of ij is equal to I plus j. In this case, if you think about what the matrix will give you, this is alpha 1, 1, so 1 plus 1 is equal to 2. This is alpha 1, 2, so this will be 3, because it's 1 plus 2. This is 2, 1, so it'll be 3 as well. This will be 2, 2, so this is 4, and then we can carry this on forever. So this notation allows us to give different ways of writing matrices, which can be generalized for infinite matrices, because this one can go on forever. And next we'll talk about what it means for two matrices to be equal. So given any matrices, for a matrix to be equal to one another, we need to have all of the elements being exactly the same. So if A, B, C, D is equal to E, F, G, H, that means A is equal to E, C is equal to G, B is equal to F, and D is equal to H. That's all there is, and that's the only way you can have two equal matrices. The dimensions will be exactly the same, obviously, and that's just the only way for two matrices to be equal. Next, we are going to show you how to add matrices. So, first of all, the easiest way to describe it is you just add each of the corresponding numbers. So in the first example, 1, 2, 3, 4 plus 5, 6, 7, 8, 1 corresponds to 5, so you add them, so you get 6. 2 corresponds to 6, so we add them, we get 8. 3 corresponds to 7, that's 10. And 4 corresponds to 8, that's 12. Subtracting is exactly the same, except you subtract the second one from the first one. So 5 minus 1 is equal to 4, 6 minus 2 is equal to 4, 7 minus 3 is equal to 4, and 8 minus 4 is equal to 4. The next thing we're going to look at is multiplying by a scalar. A scalar is a number that's not a vector, so it will just be a number in front of it. And the way we do this is we just multiply every entry by that number. So 5 times by 1, 2, 3, 4 is the same as 5, 10, 15, and 20. All we did was multiply every single entry by 5. The next thing we're going to look at will be how to multiply two matrices by each other. And now, I'm going to do this on square matrices, but as a general rule, you can only multiply matrices if the columns of the first matrix are equal to the rows of the second matrix. Otherwise, you won't be able to multiply, and you'll see why. So if we do 1, 2, 3, 4 times by 5, 6, 7, 8, the general method is you take this row and you do the dot product of this row with that column. So 1 times 5 plus 2 times 7, which is 5 plus 14, which is 19. Then, to find the next entry, we do the first row and the second column, because this is the first row and the second column. 1 times 6, 6, plus 2 times 8, 16, totals to 22. Now to find the next one, we do 3 times 5, which is 15, plus 4 times 7, which is 28. So these add up to 43. And last but not least, 3 times 6, which is 18, plus 4 times 8, 32. And these add up to 48. So this is what you get when you multiply these two matrices together. Now, if we were to take the exact same two matrices and put them the opposite way around, so we have 5, 6, 7, 8 times by 1, 2, 3, 4, what do we get? We get 5 times 1, 5, plus 6 times 3, 18. So that's 23. Then for the next entry, we get 5 times 2, 10, plus 6 times 4, 24. So that's 34. The next entry, we get 7 times 1, 7, plus 3 times 8, 24. That's 31. And for the last entry, we get 7 times 2, 14, plus 8 times 4, 32. So that's 36. And what we notice is that these two matrices multiplied are not equal to these two matrices multiplied, which gives us a rule, which is AB is not equal to BA. In other words, matrix multiplication is not commutative. The next thing we need to talk about is the determinant of a matrix. So if we were to look at this, a general matrix, A, which is equal to A, B, C, D, the determinant of that matrix is AD minus BC. So you multiply the first two diagonals and you take it away from the multiple of the second two diagonals. So we have the matrix 1, 5, 7, 3, and we call that matrix B. The determinant of the matrix B would simply be equal to 3 minus 35, which is equal to minus 32. The determinant can have negative values. If the determinant is 0, then that's a special case and we call it a singular matrix. And what a singular matrix is a matrix which does not have an inverse, which shows how determinants are important with matrices because it shows that they're singular. So if you have a question which asks you to find an inverse of a matrix, if you find a determinant to be 0, you know that the matrix does not exist. Now, for finding the inverse of a 2 by 2 matrix, we've got a little formula, which is 1 over determinant of the matrix, in this case we'll call it A, times by the matrix D minus B minus C and A. So in this case, if we have the matrix B, which is 1, 5, 7, 3, we know that the determinant is minus 32, so the inverse of this matrix is 1 over minus 32 times by 3, minus 5, minus 7, and 1, which we can work out ourselves. This just becomes a matter of multiplication by scalar. One other thing we need to talk about is the identity matrix. So, identity matrix literally looks like this, 1, 0, 0, 1. And the special property that it has is we multiply anything by the identity, which we mark as I. Let's say we have matrix I times matrix A. That's same as matrix A times our matrix I, which is equal to just A. So whatever we multiply by I, it stays exactly the same. It's like 1 of matrix algebra. We also have diagonal matrices, and they're matrices such as 3, 0, 0, 3. This does not necessarily have to be same values. It can be 3, 0, 0, 4 as well. But the point is, a diagonal matrix has only non-zero values within its diagonal. And the identities and diagonals carry on to different dimensions. So, for example, a identity matrix for a 3 by 3 look like this. And you can see how the 4x4 would look and the 5x5. Same thing with diagonals. So that concludes this video. Hope you enjoyed it, and I'll see you whenever.